Question 6.1. Explain how ions are accelerated, detected, and have their abundance determined in a time-of-flight and mass spectrometer. Well, let's explain all this first of all. So you introduce gaseous particles into this time-of-flight mass spectrometer. Now, at the moment, they've not got any charge on them. So what you do is you bombard them with something called high energy electrons. You do that with the use of something called an electron gun, which is a hot wire. The hot wire releases electrons, high energy electrons. Then they bounce into the particles. They collide with the particles and knock further electrons off. So the particles, now the gaseous particles, have an electron removed and they end up with a plus charge. Now you've got ions, atoms that have got a plus charge now, so particles with a plus charge because they've had electrons removed by bombarding them with other high energy electrons. Now you've got positively charged particles. They can be accelerated. They're accelerated towards plates with holes in them, and the plates are charged minus, so they're negatively charged plates, and the plus charged ions, they're atoms that have had electrons removed. An electron removed form a plus ion. These plus ions, because they've been particles, atoms that have had an electron removed by these high energy electrons being bombarded into them. These plus ions then get accelerated towards some plates that are negatively charged. The positive ions get attracted to the negatively charged plates. They go through the holes because the plates have got holes in them, and they hit something called a detector plate. When they hit a detector plate, the plus charged ions accept an electron from the detector plate. And in accepting an electron from the detector plate, that makes a current, and we can measure the current. It makes an electrical current. So the plus charged ions turn back into atoms by accepting electrons and creating a current, an electrical current. Depending on the size of that electrical current, we know how many there are. Abundance means how common they are, how many there are. So the ions are attracted to negatively charged plates. The ions detected by gaining electrons from the plate. So when they hit the plate, the plus charged ions get their electron back and turn back into atoms, and their abundance, their amount of them, is found out by the size, the current that's detected on the plate, or the number of electrons gained on the detector, that is. So when they hit the detector, positively charged ions get their electron back, and depending on how many hit the detector plate, then we can detect the current flowing, and that tells us how many have hit the detector plate. Calculate the mass in kilograms of a single 52 chromium plus ion. So the chromium plus ion has had an electron removed, and it's going to accelerate down this plate, hit the detector, and then the plus ion will gain an electron, make a current on the plate, and we can work out, depending on how many electrons or what kind of current, the size of the current, when these hit the plate, we can work out how many of these are hitting the plate. Assume the mass of 52 chromium ion is the same as a 53 chromium atom. But it's only had one electron removed and becoming plus, and electron mass is negligible, next to nothing, so that's fine. So 52 chromium, so 1 mole is 52 grams. So that's what the 52 is. So 52 grams of chromium is got a mass is 1 mole. So 1 mole, to get it into kilograms, it wants it in kilograms. To turn grams up into a high unit value of kilograms, I divide by 1,000. 52 divided by 1,000, 0.052 kilograms. Now I want the mass of one of these particles. So I know Avogadro's number is the number of particles in a mole. So 52 grams of this, or 0.052 kilograms of this, of our 52 chromium ion, contains 6.022 times 10 to the power of 23 particles, Avogadro's constant, Avogadro's number. So if that's the number of that's the mass of 1 mole, and 1 mole contains that number of particles, if I divide 0.052 kilograms by 6.022 times 10 to the power of 22, I find the mass of one particle in kilograms, 8.6 times 10 to the minus 26. In a time-of-flight mass spectrometer, the kinetic energy of a 52 chromium ion was was 1.269 times 10 to the minus 13. So now I've got the kinetic energy, and it also gives me this equation. Kinetic energy is half mv squared, where m is the mass of one particle in kilograms. So I've now got the m as well. So let's get rid of the half first of all. Let's multiply both sides by 2, and that'll get rid of the half. So 2 times 1.269 times 10 to the minus 13 equals just mv squared. The mass is the mass of a particle, which got me to work out before, 8.6 times 10 to the minus 26. So 2 times 1.269 times 10 to the minus 13 equals 8.6 times 10 to the minus 26 times v squared. Divide 2 times 1.269 times 10 to the minus 13 by 8.6 times 10 to the power of 26. That equals v squared. A square root it at 1.71 times 10 to the power of 6. And it's in meters per second. Bromine has 2 isotopes, okay, in approximately equal amounts. In a time-flight mass spectrometer, it forms ions Br2+. In other words, a Br and a Br have joined together. Yes, they become plus charged, so they've lost an electron. That's not going to change the mass. It's only going to be a negligible change in mass. An electron being removed, an electron has negligible, next to no mass. So what combinations could we have? Well, we've got the 2 isotopes. We've got 79 and 81, 79 Br and 81, and they're in equal abundance. That means they're in equal amounts. So what combinations could I have? I could have 2 79 Br atoms coming together. I could have 2 81 Br atoms coming together. I could have a 79 Br atom combining with an 81. So this one's on the left and this one's on the right, and they'll join together. Or I could have the 81 on the left and the 79 on the right, so I could have that combination as well. So I've got 25% of each of these combinations. So 25% of 79 two 79s, I've got Br2. 2 79s will be 158. So a Br2 with 2 79 atoms in there, I've got a mass of 158, and I've got 25% of that. I've got 2 81 atoms, so combined Br2, 162, 25% of that. I could have a 79 atom joining with an 81. 79 add 81 is 160, and I've got 25% of that. Or I could have them the other way around, an 81 joining with a 79 to give a mass of 160, 25% of that. So I've got 25% is 158, that's 2 79 Br atoms coming together. I've got 50% is 160, that's a 79 atom coming together with an 81 atom, or an 81 atom coming together with a 79, so I've got 25% of each, 70, so both have the same mass, 160, so I've got 50% of that, and then I've got 25% of 2 Br 81 atoms coming together at 162. Okay, a sample of xenon, mass 131.1, so that's the average. So when I work out the average from all of these different isotopes, the sample consists of 4 isotopes. The abundance of 3 isotopes are shown in table 3. The data for one of the isotopes is missing, so I've got to calculate what the percentage abundance is for this. So I know that the average of all 4 of them equal this. So when I've got percentages, I always imagine, I think it's easier to imagine that I've got 100 particles in my sample. Why not? I've got 100 particles in my sample. So for this isotope I've got 28 particles, for this isotope I've got 25 particles, for this isotope I've got 27 particles, and then I've got a certain number of particles of this. So I work out the number of particles of this that I've got. That's what I've got to try and work out. So my abundance is 100, so this one, the abundance, the percentage abundance is 100, take away 28, take away 25, take away 27, I've got 20% of this. So 28% is this one, 25% is this one, 27% of this one, and by subtraction, the remaining percentage must be 20%. So all of these add up to 100%. So I don't know what mass this is. That's what I'm trying to find out, the mass of this xenon particle. Its mass number, and I don't know. So let's give it a letter. Let's give it the letter M. I'm imagining that I've got 100 particles. So what mass are 129 xenon? Well, I've got 28 out of the 100 particles. Out of 100% or 100 particles, 28 of them have got a mass 129. So their total mass is 28 multiplied by 129. So those particles, I've got 28 particles, mass 129, so 28 times 129 tells me the total mass of these particles. I've got 25 particles, mass 131, so if I multiply 25 by 131, it'll give me the mass of all of these particles. I've got 27 particles, mass 132, if I multiply 27 particles, each of a mass 132 together, it will give me the mass of all of these particles. I don't know the mass of these particles, but I know that I've got 20 of them. So 20 multiplied by the mass, which we're calling m, which we don't know, is 20 times m. Now all of these total masses added together is the total mass of all of the 100 particles. If I divide by the number of 100 particles, which is 100, divide by 100, then it'll give me a value, an average value, except that it won't quite because I've got m. So what I'll do is, I tell you what, I'll take the divide by 100, I'll take it across the other side, and I'll multiply the 131.41, which is the average, the mass of all of the particles all together divided by 100. I'll multiply this by 100, so 13141 equals this value, 28 times 129, which is 3612. 25 times 131 is this value, 3275. 27 times 133 is 3591. 20m is just 20m. And I'll take all of these numbers across to the other side and subtract them from 13141. So 13141, take away 3612, take away 3275, take away 3291 equals 20m, and 2663 equals 20m. So divide both sides by 20 to leave m. M is 134. Now it's got to be a whole number because these mass numbers must be whole numbers, because that is the mass of, that's the number of protons plus neutrons in an atom. The mass number, the protons and the neutrons have atomic masses of 1 each, and so they have mass within the atom, and you can't have odd numbers of protons and neutrons in an atom, so it's got to be a whole number. So I've rounded up to the nearest whole number.